Okay, great. So hello, everyone. So today what I'm going to be talking about is kind of one of the technical topics that's been kind of fairly important to a lot of the Ethereum research that we've been doing over the last couple of years. And I think a lot of the developments that we're going to do in the next couple of years. So this is very relevant to Ethereum 2.0, though it's also a big part of an effort called Ethereum 1.x, which is a set of kind of shorter-term scalability upgrades that we're planning to add to the Ethereum protocol. And stateless clients are also a concept that's applicable far beyond Ethereum, potentially to in Bitcoin or any kind of blockchain. In some cases, even systems that are not blockchain, though probably will focus more on kind of the blockchain and Ethereum context, at least for this presentation. So start off with a couple of reminders. So we can think of processing a block in a blockchain as being a state transition function, right? So the idea here is that we think of this kind of object that we call a state, where the state consists of everyone's balances. In the case of Ethereum, things like smart contract code, smart contract storage, account public keys, basically all of the information that's needed to process transactions. And then a block contains a bunch of transactions, and processing a block basically means you take some previous state, then you process a block, and you get some new state, right? So like, for example, if the previous state is that Alice has 50 coins and Bob has 50 coins, the block has one transaction that transfers 10 coins from Alice to Bob, then your new state, state prime, is going to be the state where Alice has 40 coins and Bob has 60 coins. Sometimes a block is not even valid in the context of a particular state. So like, for example, if the state is that Alice has 50 coins and Bob has 50 coins, and you create a block where Alice gives Bob 100 coins, then that block is not valid. But if the state had said that Alice has 100 coins, then the block would be valid, right? But we can kind of not talk about validity. We can just think about it in terms of transitions and in terms of what the current state is. So in Bitcoin, for example, the state is something that exists kind of in the client in the database. So there is kind of the unspent transaction output set, but it's not kind of directly linked to in Bitcoin blocks or Bitcoin block headers. In the Ethereum case, the state is stored in Merkle tree. Specifically, it's stored in what we call a hexary Merkle Patricia tree. And the root hash of the state is stored, and this a 32-byte hash of this entire data structure that contains all of the accounts, all of the storage keys. The root of this is basically stored inside of the block header, right? So if you have the block header, then the block header contains a hash that gives you all the transactions. It contains a hash that gives you all the receipts. It contains the hash of the previous block, because that's how all blockchains work. And it contains this hash of the state. Only a small portion of the state gets read or written to in every block, right? So every block only makes a small number of modifications. The state is huge. The number of modifications is much smaller. And so the state does change, but the number of hashes that you need to recompute is kind of much smaller, right? It's basically for every one update that you make, you only have to make a login changes to the this state kind of hash data structure. And if a block reads one account, you only need login hashes because that's just a Merkle proof. So stateless clients, right? So a stateless client is a different kind of full client. So this is a fully verifying client. So even if there's a 51% attack, there's no way that you can fool a stateless client into thinking an invalid chain or an unavailable chain actually is valid. But instead of the client holding the entire, like this entire set of everybody's balances, code, and everything else, the client just holds the state root, right? The client just holds this 32-byte hash that represents the entire state. So if we think of the original state transition function, the state transition function that takes as input a state, a block, and outputs a new state, We can think of a stateless client as processing a kind of parallel state transition function, where you have the state root, the block, and the new state root. Now, the block by itself and the state root by itself don't give you enough information, right? So, like, for example, if your block contains one transaction that transfers 10 coins from Alice to Bob, well, there's a whole bunch of different accounts in the state. The state root is just a 32-byte hash, so you can't just get that information from the state root and from the block. And so we add a witness. And a witness is basically the portions of the state that actually do get read and modified in that particular block, along with Merkle proofs. Right? And I'll talk later about how it could be different kinds of proofs as well. Right? So basically, normal clients, it holds the state, takes in a block, and modifies the state to get a new state. Stateless clients only holds the state root. It asks for a block plus a witness, and it gives you a new state root. Or it updates its state root to store a new state root. So benefits of this, right? One benefit is near zero initial sync time, right? So if you have, say, the chain of block headers and you're willing to trust the chain of block headers, then you can start processing and kind of verifying new blocks pretty much immediately. Clients can validate blocks out of order. So they could validate the latest block first and then move backwards, or they can only validate particular blocks if they hear a fraud proof or if they hear an alarm. So you don't actually have to process blocks in order of first and then second and then third, because every block processing is just this kind of function where all you have is just that you're plugging in or that you're maintaining is this state root. You can kind of jump around and process blocks in whatever order you want. No disk access, so you don't need a solid state drive. It's HDD friendly. Fraud proof friendliness, so if you have stateless clients, you can also verify fraud proofs. And in an Ethereum 2.0 sharding context, stateless clients are basically mandatory because nodes get kind of rapidly reshuffled between different shards. So like one moment you might be on shard number 2047, then suddenly you get reshuffled to shard 45, and then almost immediately you have to verify a block from shard 45, and you just don't have enough time to download the entire state from shard 45. And so how would you verify it? Well, you would ask for a witness and you would verify it statelessly. So it's also potentially more secure against certain kinds of attacks. I mean, especially in cases where disks are fairly slow. So a lot of benefits. Some statistics, right? So just for notation, we'll use N to refer to the total size of the state. So this is the total number of accounts and contracts and storage slots and all of this stuff together. And K is the number of objects that get access in a block. So approximately speaking, in Ethereum blocks, N is around 2 to the 30 and K is around 2 to the 10, right? So N is about 1 billion, K is about 1,000. The witness size, so the size of the Merkle branches for all K of these objects, it's roughly in the objects themselves plus these Merkle branches that have K times the log of N over K chunks, right? So if you're just proving one chunk, so if K equals 1, then the witness size is a log N chunk, where a chunk just means a hash, so it's 32 bytes. But if you have more than one branch, then you can make a bit of savings, and you can kind of combine the parts of the Merkle branches that are redundant with each other. And so instead of K times log N, it's K times log of N over K. In practice, it's about, assuming a kind of optimal Merkle tree is about 600 bytes per access. So this is just plugging into this formula, assuming these numbers. And so a witness becomes about 600 kilobytes. There are grinding attacks on the Merkle tree. So basically, if you imagine an attacker just generates a whole bunch of account addresses that are extremely close to each other and sends like a very small number of coins to all of these addresses, and then creates a transaction that tries accessing all of those addresses, then because you have a whole bunch of accounts really close together, but like the attacker could kind of grind those addresses, and instead of the depth of the tree being 30, the depth of the tree in that particular position could go up to say 60 or 80, right? So grinding attacks could, in the worst case, expand this to maybe about 2,000 bytes per access. So this is roughly where stateless clients can kind of get us with the current technology. The bad news is that the current Ethereum protocol has kind of very mispriced gas schedules for this, right? So basically, the problem is that you can have a block that kind of does calls into a whole bunch of different accounts. The gas limit is 12 million. The gas cost of a call, including overhead, is 800. 12 million divided by 800 gives you 15,000 calls. And every call can call into a contract that has a really huge 24 kilobyte code. Plus, we don't even, right now, we're not even using an optimal Merkle tree. We're using a hexagonal tree instead of a binary tree. So the witness is 3,000 bytes instead of 600. So the total size is going to be 15,000 times 27,000, 405 megabyte witnesses, which is just horrible, right? So there's a bunch of changes to this. One of the important ones is code Merkleization. So we store the code as a Merkle tree instead of just this big chunk. Changes to needs to be more expensive than 800 gas, and switching from a hexagonal tree to a binary tree. And so we can get to a situation where the worst case witness size is going to be a couple of megabytes. Now, so we have people that are actively working on some of these changes, and potentially, if all of these things get implemented, it will actually be possible for a client that hasn't yet downloaded any state information, so a client that's just connecting for the first time, to verify just any block in the blockchain with this extra witness size of average case about 600 kilobytes, worst case a couple of megabytes. I'll also add here that, once again, stateless clients are not just an Ethereum thing. So in the Bitcoin context, there's something called a U-Tree-XO, which is basically a stateless client. So a lot of broad interest in this kind of methodology. Challenge, right? So the problem is that 600 bytes average case, 2 kilobytes worst case is actually not that nice, right? It's in 600 kilobytes, like 2 to 5 megabyte witnesses, but right now Ethereum blocks are about 50 kilobytes. So can we try to bring the witness size down to something closer to the block size instead of being 1 to 1.5 orders of magnitude larger than the block size? There's two paths to this. One is snarking Merkle trees, and the other is vector commitments or polynomial commitments. A path is fairly easy to explain. It basically says that, okay, you imagine you have a witness that contains all of these Merkle branches, and you're just going to create a snark or a stark that proves that there exist Merkle branches for a bunch of values. So instead of providing Merkle branches directly, we provide a proof that just proves that these Merkle branches exist and they're out there. And if you do that, then you can replace all of these, most of these, 600 kilobytes, basically everything except for the values themselves, with just one single short proof. If it's a Groth 16 snark, 150 bytes. If it's a Blanc, half a kilobyte to a kilobyte. If it's a Stark, 50 to 150 kilobytes, still a huge improvement. Now, second approach, vector and polynomial commitments, right? So, quick math overview. A polynomial commitment is a special kind of hash of a polynomial. So a polynomial is this big thing. It has a whole bunch of coefficients. It can contain a lot of information. And we create this kind of hash of that polynomial where that hash has extra properties, right? So one of the main properties is that if you give someone a commitment of P and you give them some coordinate Z, then if the prover has the actual polynomial P and they have a coordinate Z, the prover can provide an opening proof Q. And if the verifier has this opening proof, they can take that proof and they can use that to prove that P of Z actually equals A, right? So basically, if you have the hash of a polynomial and you have this opening proof and you have which coordinate you're trying to prove, the verifier can actually verify that the polynomial at that coordinate actually equals that value. So you can use polynomial commitments as an alternative to a Merkle tree, right? So if you have a bunch of data, D is 0, blah, blah, D of n minus 1, you can just represent that as a polynomial where the ith element in the data just equals the polynomial evaluated at point I, right? And it's actually very easy to construct polynomials like this. So you can use a Lagrange interpolation, for example. I mean, there's a lot of algorithms for this. Now, you might want to ask, well, why do we do this, right? And we'll talk about this. First, very quick overview into kind of the two main families of polynomial commitments. So case commitments, basically the idea here is that you have a trusted setup where you have, and this is all done with elliptic curve points. You have a secret number S, and your setup consists of a bunch of points. So you have the generator G, then you have G times S squared, G times S cubed, blah, 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 all the way up to G times S to the D. And you have G2 times S. So this is in the G2 group. So the idea is basically that if you want to encode a polynomial that has some coordinates, you would basically take the first coefficient multiplied by G, take the second, you take the 0th degree coefficient multiplied by G, you take the degree 1 coefficient multiplied by the points of G times S, and then the degree 2 coefficient multiplied by G times S squared. So what we're basically doing here, right, is that you're basically creating a point that equals G times the polynomial evaluated at S. Now, nobody knows S, which is really important for security, right? That's the kind of toxic waste that you have to forget after you generate this trusted setup. But then the way that we prove, do an opening proof is basically if you want to prove that for some P of Z equals A, you do it by proving that P of X minus A kind of has a 0 at Z. And to prove that, you basically prove that X minus Z is a factor of P of X minus A. And you do that by, well, providing P of X minus A divided by X minus Z, right? So if you can provide a polynomial such that you take that polynomial, then you multiply it by X minus Z. And then you add A, then you actually get your P of X, and this actually basically proves that this P of X actually is a polynomial that equals A at this particular coordinate. And you can verify this equation with elliptic curve pairings, right? So you can basically, like here what we're doing is we're taking Q, we're multiplying it by X minus Z, or actually then we're subtracting A, and we're basically checking whether or not you get P back. Dankrad, one of our researchers, recently wrote an article that goes into this in more detail, a lot of really interesting and great math. Fry is another alternative. This is a purely hash-based polynomial commitment scheme, so post-quantum secure, which is really nice, potentially faster to prove. The idea basically is that if you have a polynomial P, then you kind of define these two polynomials, evens and odds, that are basically one of them kind of captures only the even degree coefficients, the other captures only the odd degree coefficients. And so these are both degree n over 2 polynomials in X squared. And then you just kind of randomly combine them together. And the idea is that if this procedure where you kind of split P in half and then you randomly combine the halves together, it has degree n over 2, then you know that P of X almost certainly has degree n. And then you just kind of repeat this procedure recursively, right? And in order to check that kind of every step is equivalent to every next step, the prover just basically provides a whole bunch of Merkle branches and tries to prove that it's kind of true at almost, or the equation is true statistically at almost all coordinates. Once again, I wrote some blog posts on Stark's very interesting topic, including on Fry. Highly welcome people who are trying to kind of learn more about this. But zooming out again, basic summary, right, is that you can, in a whole bunch of ways, create this thing that's basically this kind of hash of a polynomial that you give to someone, where you then have this ability to create these opening proofs that kind of prove that that polynomial equals a particular value at some particular position. Multi-openings. So this is basically, we get to the point where we actually learn why polynomial commitments are useful, right? So let's say instead of wanting to prove one value, wanting to prove P of Z equals A, we want to prove P of Zi equals AI for a whole bunch of values, right? So you want to prove a whole bunch of values at a whole bunch of positions. You can do this with only one witness. And the basic idea here is that instead of kind of subtracting A and dividing by a polynomial that equals 0 at one point, you kind of subtract an interpolant, and an interpolant is this polynomial that equals the point that you want at all of the coordinates that you want. So this interpolant is the degree less than k polynomial, where evaluated at every Zi actually gives you AI for every one of these coordinate pairs. And you basically, if the reason why you do this is because if P equals AI at every Zi, then P, because the interpolant equals AI at every Zi, P minus the interpolant is going to equal 0 at every Zi. And so P minus the interpolant is going to be a multiple of the smallest polynomial that equals 0 at every Zi, so that's Z of X. So then you just have this kind of one equation, and the verifier can just verify this one equation, right? So once again, zooming out, result of this is basically that unlike Merkle branches, where you need a separate Merkle branch for every value, with polynomial commitments, you can create this multi-opening proof, and you can prove a whole bunch of values that with basically just one witness, right? So you can see how this is a really valuable technology, potentially for making stateless clients better. Unsolved problem. So one of the problems with this scheme, unfortunately, is that Merkle branches kind of have this really nice property, or Merkle trees, which is basically that they're cheap to read, but they're also cheap to update, and it's cheap to update all the witnesses, right? So if you imagine a Merkle tree containing the entire state, then one value gets updated. Updating one value is cheap because you only have to update kind of log n hashes walking up the tree from that value to the top. So this is like very nice for basically nodes that are trying to create witnesses. K commitments are terrible at this, right? Because if you have a polynomial and you update that polynomial's evaluation at one coordinate, then that ends up changing every witness. That ends up changing every one of these, like P minus something divided by X minus some coordinate. So basically, the intuition is that kind of it seems as though we want to find some kind of mechanism for generating these witnesses where you want them to be kind of computable from data in some tree-like structure, right? So you want them to be computable from data that kind of gets stored in some structure where if you modify the data in one position, then you only need to make log n. I mean, we could potentially sacrifice a bit and say polylog n changes to the data and generating a witness. And so reading this kind of value also requires reading the data in a logarithmic or possibly polylog number of positions. So challenge, we still haven't yet figured this out, open problem. And challenge 2 is the trusted setup size, right? So the Ethereum state already around 2 to the 30 objects. We probably want to budget for something like 2 to the 36. Trusted setups, we've done them up to 2 to the 28. And the bigger they become, the more inconvenient they become, and the more trusted they become, which is really annoying. Technique 2, Verkle trees. So Verkle tree is basically just trees of vector commitments or just trees of polynomial commitments, right? So basically we kind of combine the two schemes together and we say, well, we're going to have, instead of having just a Merkle tree or just one polynomial commitment, we're going to have a tree of polynomial commitments. And so if you want to prove one element, you would basically just provide that element. Then you would provide these kind of commitments that are in the middle. And then you'd have to provide a proof that the element is a member of the first commitment, then a proof that the first commitment is a member of the second commitment, then a proof that the second commitment is a member of the third commitment. And so the witness, instead of being, say, 32 hashes long, the witness might be 2 points, so it might be, say, 96 bytes per element. Cost of updating witnesses minimal. Cost of generating proofs, it turns out, like if you have each of these polynomial commitments has depth 1024, then it's 1024 times k field operations, and it turns out you only need just 1024 curve operations. The verification cost, k pairings, if you do it naively, which is actually kind of expensive, but with some extra work, you can push it down to 3 pairings, right? So this is another kind of recent approach that we've tried to take to just cutting down the witness sizes. It's not perfect, so you still have like about 96 bytes per element, but that's still much less than 600 bytes or even more in the worst case. And then technique 3 is just snarking Merkle trees, as I mentioned, right? So you basically just make a snark that proves that there's a whole bunch of Merkle branches that prove some specific set of values. The benefit is that this is a kind of overlay onto a Merkle tree, and so there's no sacrifices in kind of witness updating, for example. Another benefit is that it's quantum safe. It's recent numbers from Starkware with their kind of new special purpose hash function. They can prove 10,000 hashes per second, which would be about 2 seconds to compress an Ethereum block witness. So actually quite within the range of viability. That's on, I believe, a either 4, 8, or basically a fairly powerful laptop, by the way. So very well within the range of consumer hardware. 2 seconds to generate a proof. So seemingly an ability, right? And also, there is this other recent idea that we've had that some researchers have proposed around using this protocol called GKR, which basically tries to reduce the cost of hash verification down to 3 constraints per hash plus a bunch of field operations. So, like very, very cheap hash calculations. So, summary, I guess stateless clients are great. Stateless clients can solve a lot of problems. They can solve very big problems in terms of the amount of storage that Ethereum nodes require. They allow Ethereum clients to sync pretty much instantly. They allow kind of different syncing and verification strategies. They open up kind of this entire full trade-off space that's kind of somewhere in between light clients and full clients. They can work without needing like power, like a lot of disk space or a lot of disk access. And there's a bunch of fancy arithmetic techniques that allow us to kind of cut these witness sizes down to the point where kind of the extra data that stateless clients need to download is actually not that much. But still research and still kind of a lot of refinement required. And this is something where, we actively welcome more kind of input and help from the academic research community. So thank you.
And thank you very much, Vitalik. Thank you, everybody, for joining us. Just a very quick shout out to everybody. Thank you for joining us. We are at CESC 4th day, obviously headlining and starting the day off with Vitalik. I hope everybody enjoyed his presentation and everybody enjoyed him sharing his thoughts, especially around the different techniques and everything. We're just going to go into a very short Q&A. We're going to have a look at the questions. Vitalik, if you can hear me, I think the first question everybody wants to know, we're getting this quite a little bit. Is there anywhere we can share? Are you going to share the slides anywhere? Is there anywhere where people can have a look at the slides after the presentation?
Sure, I'll be happy to. I mean, I'll tweet them right after we finish this. How about that?
Nice. All right. Yeah, you're getting a lot of thanks from everybody. The next question which we have is from actually one of our viewers, within Brella. And John here asks, what are your thoughts on the Ethereum Bitcoin bridges like Keep Network? Do you think they actually benefit the Ethereum community in any way?
I think Ethereum Bitcoin bridges are really valuable, and I've said that many times myself. I think the main challenge in some of these bridges is basically kind of trust minimization. So we want to avoid kind of creating trusted intermediaries that end up kind of holding hundreds of thousands of people's Bitcoins where it ends up not being clear how secure they actually are. So I know there's efforts that are trying to do this, like I know TBTC is trying to do this, and there's some other projects that are trying to do this, but still more work required. Hope it keeps going well.
Yeah. I think one question, and thank you for the answer as well. I'm going to skip one question. It's a timeline question. I think you get that quite a bit. We're going to move on to something a little bit more since we're talking about the development side of things. Curious question from Edward here, again, inside Brella as well, where essentially the event is streaming. What's your current involvement on the development side of the protocol? And I think the main question is that, are you more focused on research side or are you more focused on the development side right now? Or still both?
I mean, I've definitely always been more focused on the research side and kind of the earlier half of the pipeline. Though I do think that Ethereum 2.0 has made like a lot of huge progress in the last couple of years, and like you can clearly see how it's moved from being a research project to being a development project, right? Like we now have the Altona multi-client test network, and we're going to have phase 0 kind of coming out on mainnet fairly soon. So ETH2 is by itself has definitely switched from being a research task to being a development task. And so, in terms of what that means, I'll end up being focused on. And there's definitely still some things, but it's more kind of a bunch of things in different places, I guess.
Interesting. Actually, since you're talking about ETH2, Edward actually has a follow-on question. If a couple of people, I think you get that quite a bit. But, for the sake of the audience, I'm going to ask you anyway. Can you maybe elaborate, especially after this presentation, can you elaborate a little bit more about the next milestones in Ethereum, and maybe a timeline for Ethereum 2.0. I know you've talked a lot about this already, but I think let's answer the question for everybody's benefit of milestones in the next 6 months, basically for the rest of 2020.
Sure. So right now on the Ethereum 2.0 side, we obviously already have the Altona multi-client test network, which is the kind of running with mainnet parameters. In a few weeks, we expect to launch another test network, and that test network will just have some kind of updates in terms of like basically the user experience will be kind of basically the same as we plan it to be on mainnet in basically every way, and a couple of kind of fairly small upgrades. So one more test network. If the test network runs smoothly for some amount of time, the next milestone is, of course, Ethereum 2 phase 0 launch on mainnet. And that's definitely looking within the 6-month window. And then after that, there's obviously phase 1, but phase 1, which includes not just a proof of stake, but also like starts to include sharding for data. That's looking definitely outside of the 6-month window at this point. Outside of ETH2, I think it's also important to mention, first of all, ETH 1.x, so stateless clients, kind of different state management strategy as kind of shorter term Ethereum upgrades, and continued ongoing work, some things coming in the next 6 months, some things not. So that's a kind of parallel track. Also layer 2 protocols. So we have ZK rollup already, right? So on mainnet, we have Loopring and we have ZK Sync. And those are rollups for Loopring is a decentralized exchange and does payments. ZK Sync does payments. And so those two can both do, well, rollups in general can do theoretically up to somewhere around 2,000 to 300,000 transactions per second on the Ethereum network. And that's a kind of load that's theoretically achievable today if everyone switches to these rollups. But the weakness of ZK rollups right now is that they're only good for like a very small number of specific use cases. So payments and token transfers and DEX is like probably the biggest ones. But if you want like general purpose EVM smart contracts, you probably want to look at optimistic rollup. And optimistic rollup, it's definitely looking very hopeful that we'll see optimistic rollups in a 6-month window as well. So carefully watch the teams that are doing that too.
Okay, so I think since we've just asked the question, somebody has asked about the question. John actually and a couple of people also have a follow-up question. I'm just going to kind of like mesh all the entire question together, given that we've got about 8 minutes left in the Q&A. Is there first question is there definitely a proof of stake for Ethereum 2.0? And I think the follow-on question to that as well is, when we talk about proof of stake, the other question is there any interest to adopt a wider range of supported curves for ETH2 to allow additional functionality?
So for question 2, by curves, you mean like elliptic curves?
Yes.
Okay, so for the first question, yes, Ethereum 2 is a proof of stake system, and Ethereum 2 phase 0 is kind of the start of Ethereum's switch to proof of stake, which will take multiple stages, but phase 0 launching is the first stage.
As for multiple curve support, there are EIPs that are in progress to add support for more curves. The basic challenge is that it's a kind of trade-off of, I guess, functionality versus, I guess, complexity. So the existing, I mean, there's a lot that you can already do even within just the BN128 curve that's supported on Ethereum already. But if we support other curves, then you can do kind of depth 2 and potentially depth 3, kind of recursive snarks. And there's a lot of value in those kinds of constructions, especially if you want to get privacy and scalability at the same time, which is something that, like, for example, I know Aztec has been doing a lot of hard work on. So I definitely, it's something that we are kind of working towards. It's just a question of priorities at this point, right? Like, I think the main reason not to focus on it is basically just because, like, people really want scalability and they really want ETH2 and they want kind of relief from high transaction fees and so forth. And so, like, those things are definitely higher priority for us than kind of supporting some like kind of advanced elliptic curves in more optimized ways. But like, we have a large team, and there's people that have been very actively pushing that forward as well.
Nice. So kind of a fun question right now. I think when it comes to Ethereum, something that's been getting quite a bit of buzz in the last 1 month is actually the Reddit competition, which I'm definitely sure you're aware of. The question everybody is asking right now is that there is, how's the competition going? Do you think, in your personal opinion, there will be a submission that meets all the requirements by the month-end deadline for the Reddit competition? What are your thoughts on that one?
I think so. And so I think, kind of theoretically speaking, right, Reddit's current use of tokens is, what they want to do on Ethereum is fairly simple, right? And it feels like it's something that you can describe entirely in terms of token transfers, which is really nice because it basically means that if they want to, they can design their entire thing on top of ZK Rollup, and so it could be ready even today. But I know there's other solutions as well, so I'm definitely just looking forward to seeing what kind of submissions people end up coming up with.
Do you think probably in the short term, meaning that in the next 1 to 2 months, that's one of the things that you're probably most excited about? Or is there any other things people should keep an eye out there? There's so much going on in the Ethereum space right now.
So things that I'm excited about, Ethereum 2 Phase 0, definitely, ETH 1.x, definitely, and including, EIP 1559 and all of that stuff. Rollups, ZK rollups and optimistic rollups. Better privacy tools is another one that's coming. So I think those are probably the big ones, but there's a whole bunch of different things coming down the pipeline.
Actually, talking about the ZK rollup, do you really think it's probably one of the most promising approaches?
In the long term, yes. So in the long term, kind of the benefit of ZK rollups over optimistic rollups is that because ZK rollups rely on snarks instead of fraud proofs, you don't need to have like the waiting period for fraud proofs. So you don't need to have a 1 week withdrawal period, which is really nice for basically usability. So that's a big benefit that I see for ZK rollups. And then also, of course, you just don't have to worry about kind of infrastructure as much, and you don't have to worry about, the risk that there will be just totally no one watching for fraud and some fraudulent transaction will slip through. The main challenge with ZK rollups, of course, is that you can make a ZK snark without not that much difficulty for a kind of very structured specific applications, but making a ZK snark for general purpose computation is much more difficult. But that is, I think, kind of the next major frontier that a lot of people are going to actively move towards.
Got it. All right, we're almost out of time, so I'm just going to wrap things up very quickly. We are now, especially for people like myself, we essentially are an blockchain event organizer. We obviously keep our ears very close to the ground, and that's why we're very, very honored and very, very happy to have person like you and all other speakers join us within the Tides, which is by Block Show and San Francisco Blockchain Week. I kind of have a question for you out of fun, something the team was discussing and kind of like asking me to ask this. Given that we're all now in the online conference world, interested in doing, I know, like one fine day, if we were to do maybe like a live, instead of a live conference, it's a live development or a live developer workshop, live hackathon, which, we'll get you in to lead it. Is this something you're game for? Is this something you'd be interested in?
I mean, maybe. I guess, it depends what it is, depends what the format is, and definitely happy to participate in things.
Yeah, I kind of got forced in there. Anyway, thank you very much for everyone watching. Thank you as well for staying with us. We've got a long day ahead. For all of you who are looking for Vitalik's presentation, he'll be tweeting it out slightly later. For those of you who have maybe joined us a little bit late, especially for myself, I'm in Singapore right now, so it's nearly 1 a.m. And may miss certain parts of the Crypto Economic Security Conference, including Vitalik's presentation that happened earlier. We will essentially be putting it on demand in the Umbrella platform within the next 24 hours from now. Right, all you need to do is to go to unitize.online. If you don't have an account, sign up for it. If you already have one, just go into the schedule and click past content. You will be able to see Vitalik's presentation by tomorrow. Vitalik, it's been a pleasure. Thank you very much for your time. And for everybody else, we will be back with you shortly with Alessandro Chiesa's presentation. Thank you very much.